Hi, this is Pablo Muñoz. I am a research scientist at Intel Labs, and today I am presenting our work, Automated Supernetwork Generation for Scalable Neural Architecture Search, at the first International Conference on Automated Machine Learning. Let's start with an overview of our work. A successful approach in neural architecture search is to create a supernetwork using weight-sharing approaches on a based architecture. Once the supernetwork has been trained, we can then search for high-performance subnetworks. Unfortunately, generating and training supernetworks for neural architecture search using arbitrary neural network design spaces can be a challenging experience. There is the need to code the main data structure for the supernetwork and include mechanisms for activating and extracting forward and backward passing on selected subnetworks. The process is often repeated when a new supernetwork needs to be generated for a different search space. Our work tackles these challenges and provides the following contributions to the AutoML community. Bootstrap NAS, a software framework that automates the generation and training of supernetworks from pre-trained models and the subsequent search for high-performing subnetworks. During the search stage, the framework is hardware aware by incorporating direct measurements collected at a target hardware or by using predictors that have been trained in advance. Here, we illustrate the workings of a simple supernetwork. The goal is to discover smaller and more efficient architectures for a particular hardware configuration, while maintaining accuracy requirements. When all the layers of the supernetwork are activated, we have a model that has a particular performance. The goal is then to activate smaller subnetworks that are more efficient than the original model. To accomplish the goal of discovering smaller and more efficient architectures, we might have to reduce the number of channels in some layers, thus affecting the width of the model. We can also try to remove complete layers or blocks, thus producing shallower models that might be more efficient. There are a few challenges when generating and training supernetworks from arbitrary-based architectures. In most of the cases, the code for a supernetwork that produces a different search space has to be written from scratch. Specialized mechanisms are required for activating and extracting child subnetworks. Specialized training loops might be required for each supported supernetwork. Can we automate and generalize supernetwork generation, training, and the subsequent search for high-performance subnetworks? We present Bootstrap NAS, a software framework that automates the generation and training of supernetworks from pre-trained models, and the subsequent search for high-performance subnetworks. Bootstrap NAS reduces the obstacles to AI model optimization using neural architecture search. Bootstrap NAS is implemented within the Neural Network Compression Framework, NNCF. Let's go over the components and the different stages of the framework. First, Bootstrap NAS receives as input an existing pre-trained model and a dataset. The model is then converted into a supernetwork by automatically inserting pre- and post-operations on each elastic layer. For example, in the case of a convolutional layer, these additional operations allows us to activate different kernel sizes or use a different number of channels, effectively creating subnetworks. Once the pre-trained model has been converted into a supernetwork, its maximal subnetwork Amax should have the same cost as the original pre-trained model on the same dataset. Our transformation from the input model to the supernetwork must guarantee this. Once the supernetwork has been automatically generated, Bootstrap NAS uses a training strategy to train the supernetwork. Bootstrap NAS implements progressive shrinking as a default method for training the automatically generated supernetwork. Other training strategies, for instance single-stage training, can also be used, and the user of Bootstrap NAS can extend the base class of the training algorithm to implement their own training strategies. The next step after the super network has been trained is to discover high-performing subnetworks. To accomplish this, Bootstrap NAS uses NSGA2 by default. However, other subnetwork search algorithms can be used. For instance, the user can pass their own algorithm using the Bootstrap NAS API. As illustrated in the figure on the right, NSGA discovers a Pareto front from which efficient subnetworks can be selected. We discussed two subnetworks in the Pareto front. We have Bootstrap NAS A, which requires less MAX than the input pre-trained model while having a drop in accuracy of no more than 1%. Another subnetwork, Bootstrap NAS C, maintains the accuracy of the input model while requiring significantly less MAX. Our goal is to provide highly extensible APIs to allow researchers to extend Bootstrap NAS with their own algorithms for super network training or super network search. Bootstrap NAS is hardware aware by incorporating measurements collected at a target hardware during the subnetwork search stage, or by using trained predictors for these measurements. Users can create their own performance estimators and provide them to Bootstrap NAS using its API. We have paid particular attention on hiding the complexity of the framework while providing the user with intuitive APIs to work with super networks and their subnetworks. As shown in this code example, we first convert the input pre-trained model into a super network, then create and use a training algorithm to train the super network, and finally, after the super network has been trained, we search for subnetworks that satisfy the requirements of the user. Automating the generation of super networks from arbitrary input architectures is a challenging and mostly open research problem. Some complex network configurations might not be supported by our framework yet. To confront this limitation, Bootstrap NAS allows the user to modify the elasticity levels of the super network, going beyond what the framework suggested after analyzing the input model, effectively enabling the adoption of complex architectures that go beyond the framework's current capabilities. We have described Bootstrap NAS, a software framework for automated super network generation for a scalable neural architecture search. Bootstrap NAS automatically generates and trains super networks from existing pre-trained models and performs neural architecture search to identify high-performance subnetworks. Our solution reduces the obstacles to AI model compression using NAS. Bootstrap NAS is integrated into the Neural Network Compression Framework, NNCF. More details about Bootstrap NAS can be found in our paper, Automated Supernetwork Generation for a Scalable Neural Architecture Search. Our code and latest results are available in our GitHub repository. Thank you, and please reach out to us if you have any questions or if you want to contribute to Bootstrap NAS.